Hello students, welcome back. Let us resume our discussion in section 3. Previously in section 3, we went through the derivative computations on log functions. For natural log functions, here we are. And for arbitrary base log functions, here we go. And then some derivatives on inverse trig functions, like these. Remember those? Now you tell me, which is more important, log functions or inverse trig functions? Of course, log functions by far. So let's go back to log functions and study some more. We're going to focus upon this kind of problems, which we call logarithmic differentiation. Here's type 1. Here's type 2. Let's take a little bit bigger font so that you can read better. So type 1, we have a humongous product or quotient or both. Type 2, we have an exponential function with variable base. So both the base and the exponent are functions. For the first problem, the base is just x, variable, but not really a humongous function. But down here, both are functions, cosine of x, log of x, apparently harder. So how do you deal with these kind of problems? Well, one step at a time. We're going to come back to this in a moment. Let's focus upon the type 1 case first. One way to handle the derivatives of these kind of things is the generalized product rule. Wait a minute, it looks like a quotient. Why product? You can change all quotient into product. Like this. Flip over denominator to the numerator by taking the negative power. This one here, fourth power, becomes negative fourth power. This one here, seventh power, becomes negative seventh power. And in return, no denominator. They all came on top. So what do we have? We have a product of 4 factors. And then we are ready for the generalized product rule. So we have 4 factors. So we have 4 bunches to be added. The first bunch has the derivative for here, the first factor. The second bunch, the second factor is a derivative. Third bunch, third factor is a derivative. Finally, the fourth factor is a derivative. First, second, third, fourth. And then add them all up. It's easy. Copy and paste, plus, 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 and then replace the first factor into the derivative. Replace the second factor to its derivative, and the third and the fourth. That's a generalized product rule. If you do it just twice, then that's just usual product rule. Now we have 4 factors, so I need 4 bunches added up. If I had 5 factors, then I'll have 5 bunches added up. Okay, that's good, and this is my preferred solution as a matter of fact. Just take one step to change everything to product, and then straightforward computation using the generalized product rule and the chain rule. But here's another solution, and this technique is called the logarithmic differentiation. Let's talk about it a little bit. Step 1, take the log. And then we can simplify this log by decomposing it. We have 4 factors here. And all the factors are numerators, well, those are multiplications. And then the log function changes multiplication to addition. How about denominator? We have 2 factors down there, and denominators are division. And what does log rule do? It changes the log rules, especially the second log rule, changes the division to subtraction. Put these together, that's what we get. Numerator, multiplication, addition, so they have plus sign. Denominator, division, subtraction, consequently minus sign. Do you see that? Numerator, positive, denominator, negative, that's it. Rule number 1, multiplication to addition. Rule number 2, division to subtraction. Put those 2 together. Apply those at the same time. Multiplications, numerator, positive. Division, denominator, negative. Alright, let's use log rule number 3 now. Put these powers up front as coefficients. This one here, you can consider this as a cancellation. Log and exponential cancel each other out. Or you can take this x out, and then you have log of e. And then log of e is actually 1, so this thing actually goes out. So either way, we get the same thing. Alright, now we are ready to take the derivative. If you take the derivative, this one here, left-hand side, this is going to be an implicit differentiation. You can take the derivative implicitly. Well, of course, you can use this formula, u prime over u, and that'll become y prime over y. But probably a better way to understand is to take the derivative implicitly. Like this. Take the derivative of log, so 1 over y, and then whenever you use the derivative formula to y, y prime pops up. So what do we have? The derivative of x is 1, derivative of this logarithm, 1 over x plus 2, and then we have to multiply the derivative of the inside, but that's 1. So you don't have to multiply by 1, but there it is. Now how about this? This is logarithm, so x squared plus 1 goes to the denominator, and then we have to multiply the derivative of the inside. That's 2x. So 2x times 4, which was there before. Now here, 7 is a coefficient that was there before. 3x minus 1 goes downstairs, and multiply the derivative of the inside. That's 3. Okay, alright, we are almost there. We want to find out y prime, right? Yeah, we are doing the implicit differentiation. So take the derivative, and then whenever you take the derivative with respect to y, y prime pops up, and then you're looking for y prime. You're solving for y prime. Flip this y to the other side, and you're going to get y prime equals to some expression like this. All good? This is the answer, yeah. But there's a bit of a problem. This one here is an x expression. This one is a y expression. Those are mixed up. It's not really ideal. So how do I rewrite? Well, y is equal to this in the original problem. So bring it back down here. Substitute back right here. And that'll give me the final answer. This y, well, the original problem. And then here, parenthesis, that's a computation we just did. Let's recap this problem. A humongous product or quotient of both. Take the log, break it up, numerators positive, denominators negative. Simplify by taking the power to the coefficient. Take the derivative implicitly. Y prime over y in the left-hand side, right-hand side, the derivative computation for each logarithm. Flip y to the other side, and then replace y back to the original problem. That completes the solution, and this method is called the logarithmic differentiation. Which method do you prefer? Me personally, I like the generalized product rule better. Let's do this one more time. Let's do it for the second problem. Let's go ahead with the logarithmic differentiation. Step 1, take the log. And then you have to simplify. Let's see, take the log. So this is a big square root, so that's 1/2 power. So 1/2 comes out. Is that clear? The square root is 1/2 power. So I can bring out this 1/2 using the third log rule. Alright, and then let's decompose this. Numerators, those are multiplications, so positive. Denominator, those are divisions, so they're negative. So that's what we get. All the factors in the numerators are basically multiplications, so they become additions. Consequently, they have plus signs. All the factors in denominators, those are divisions, So they become subtractions. Consequently, they have the negative signs. And then 1/2 was there before, so that's distributed over. Okay, now simplify. Bring down all those powers. All the powers down to the coefficient, and then simplify this log and exponential. We are ready. We can take the derivative of this. Take the derivative implicitly. As usual, we have y prime over y. Or you can rewrite like this. Take the derivative implicitly. 1 over y times y prime. And then, as usual, you're looking for y prime. That's what you do for implicit differentiation. And then in the right-hand side, just take the derivative of each. Whatever inside goes to the denominator. And then you have to multiply the derivative of the inside. The derivative of the inside is 2. Let's expand the font. And then the derivative of the inside is negative sign. And the derivative of the inside is 3x squared. So we get all these. Finally, flip this y in the denominator to the other side. Y prime equals to y times all that. And that's the answer. But not the best form. Inside this parenthesis, we have an x expression, and this y, that's a y expression. Let's go back to the original problem, and this one here, that's equal to y. So replace that y into the original problem, and that gives me the final answer. This is the same as y, and then this parenthesis is a computation you just did. So that's the logarithmic differentiation method. Take the log, simplify, take the derivative implicitly, flip y to the other side, and then substitute y back using the original problem. If you don't like that method, then here's a second method. Let's use the generalized product rule. So original problem here, and then 1/2 power is distributed over, and then all these powers downstairs, you can flip those up to negative powers. So we have x over 2 power, 4 over 2, so second power, 5 over 2 power, 3 over 2 power. You see, 1/2 power is distributed over. Okay, we are ready. Let's apply the generalized product rule. So we have 4 factors, so 4 bunches added up. The first factor becomes a derivative. The second factor becomes a derivative. The third factor becomes a derivative. The fourth factor becomes a derivative, and each derivative computation is a chain rule. And that's it. After that, you may want to simplify if you want to, but I wouldn't really bother with simplification. Just make sure the structure is correct. We have 4 factors, so 4 bunches must be added. Each bunch has to have 1 derivative. The derivatives are the first factor, second factor, third factor, and fourth factor, respectively, at each place. The others all stay the same. The generalized product rule. So once you convert OK in the first step, the next step is just cumbersome but straightforward. If you're just copying and pasting with computer, then that's really easy. Even if you have to rewrite everything, it's not going to be too bad because it's basically copying and pasting. Okay, not pasting, just copying. So we went through type 1 logarithmic differentiation, and you can avoid it if you want to. You can use the generalized product rule. In any case, we went through that technique. Which technique do you like better? Me personally, I like the generalized product rule better, but our textbook author apparently prefers the logarithmic differentiation.